In this lecture, we will deal with personalized search and social context of retrieval from web. The most of the focus will be given to recommender systems, and we will introduce the three basic categories of recommending methods, and this will be collaborative filtering, content-based recommendation, and knowledge-based recommendation. In the last part of the lecture, we'll also mention aspects of social information retrieval and how to use the information that is in social media or in the context of social environment for recommending and generally for retrieval. We'll start with a bit of history with Web 2.0. So this is the time when the static web became dynamic. So in some mid 90s, where due to the development of web, the users became to generate the content. So the content of the web was no longer just the responsibility of some admins of web pages, but ordinary users, due to web applications, started to generate the content. So far, we were interested in the basic web infrastructure for retrieval, where the basic element of information was the web page that consisted of text information, the hypertext information, so also links between pages, so graph information, and some technologies of semantic web. But we didn't completely consider the authorship of the content. And in the basic web infrastructure, this is basically not possible because it's too low level, and there are no mechanisms how to guarantee and how to support the authorship and other high level information about the resources. And this comes into play later during the Web 2 period, when there developed web applications that basically introduced new data types connected with the users and user profiles and high-level entities. So we experienced the onset of blogs and discussion forums in the 90s. Then there developed e-commerce applications, e-banking. Then later, of course, hosting services for whatever kind of multimedia and other kinds of data. Then in the first years of the new millennium, the social media started to expand, and recently we also experienced e-government services that spread quickly nowadays. Also, professional cloud services nowadays provide a range of services from the side of office services for creation of documents, through collaboration environments, video conferencing, etc. All of these web applications basically suppose that there are user profiles. So all of these services somehow register users as not as just users, but also as data entities within the environment. And here the personalization comes into place, because in such environments there is the possibility of taking also this extra information into account when searching, and the user profile could be used as another information when retrieving content, or it it can even become a recommender system, because the recommendation is based on user preferences that are somehow, depending on the application, gathered during the user's behavior, user's interaction with the application. So now we are in different situations. So we are no more in application agnostic environment, such as in the basic web infrastructure. We are now in some more application dependent area where other kinds of information take place. Of course, if the application is large enough and basically establishes another interpretation of the web as such, meaning especially the social media, for example, if on Facebook we have billions of users, basically the scale of such a huge application is very close to the basic web infrastructure. So in such an environment, it's worth to consider this environment as a completely new infrastructure for retrieval. So it's not just a small application. So it definitely makes sense to take this factor into account. Okay, so as I said, during the years, people became the part of web creation. They generated content on the data side of modeling. Users became data entities and making also graph structure within the social networks and so on. So we get completely new information that is very plausible to reuse in the retrieval process. The social media, it's a specific subpart of this evolution, because, as I said, it could be a really very large infrastructure, billions of users, and it also has specific pattern of the data types they basically assume and instantiate. When we talk about social media or social networks, we mostly think about explicit social networks like Facebook, where we really have basically known structure of the network. So the edges of the network are created by users themselves, just by adding other people as friends. So they are constructing the edges in the network, or they are posting some content. Again, they are creating nodes and linking to the nodes. So there is really explicit social network. But we also can construct social network implicitly from as implicit structure from other kinds of data. We can generate social network without the explicit activity of the users. We could generate the social network out of relational data, for example. We will talk about this at the end of the talk. What we experience in social media is two kinds of overloads: information overload and interaction overload. Here we have the problem with explosion of information, especially in the social media. Everybody can create content, not only at social media. We have blogs, YouTube, and other hosting servers, discussion forums, and so on, but mostly social networks where the content is explosively created. All at the same time, in social media, there is not only explosion of information, but also explosion of interaction, where it is really easy to create the interaction. That means the edges in the graph. So just clicking on somebody and becoming a friend means there is a new edge in the network, in the graph. Liking content, sharing content, retweeting, commenting, and so on. This not only creates the information, but also the interaction. And there is a multitude of these in social media. All in all, both of these overloads contributes to basically bad or worsening ability of classic search systems to find relevant information, because the content-based search is suddenly not sufficient, because the content is not the main information. As we already discussed in the case of PageRank, which was kind of example that not only the content, the text content is the only information, where we introduce the topology and the structure of the graph. Here it even continues into deeper consequences, because the content maybe is even less important, but the interactions maybe are more important. So maybe I do care more about number of likes than the actual content of what's liked. So yes, this is the reality of social networks. So but technically this means that I cannot only retrieve information based on the content, but also based on personalized search and based on these new types of data that appear in the context of applications that work with users and user profiles. The recommender systems are basically, or the area of recommender system is the main area that deals with personalized search or personalized retrieval of data. And from the software engineering point of view, recommender systems are not standalone systems, such as, for example, databases. Database systems can be really major standalone systems that are used by other systems, but recommender systems cannot be just standalone systems. They must be a subsystem within applications. So they act as a components of applications, because they need some environment where they live. They cannot live just in vacuum. So what is expected for recommender system is some input that comes from the environment they live in, and some output. So the input is the subject of recommending. So some information about users and user interactions with so-called items. Item is a general term for recommending stuff. So item is anything. It's just some object. It could be a product. It could be a movie. It could be whatever matter of concern. And we have profiles for both the items and the users, and of course the interaction. There are also other things like context of recommender systems, but these are application specific. We can distinguish between locality, time, seasons, other contextual properties. Okay, so this is on the input, and on the output there is of course the recommendation. So it is expected that a user gets some recommendation for items. So the main result is some top K list of items based on the method that the recommender system uses. Of course, the items in the list are somehow ranked, so we basically suppose some real value ranking or rating of the items, so the user has not only the order or just binary recommendation, but also rating of the items. And the last step of the output is some presentation recommendation to the user, because this is not so easy thing, because many of the applications really stress that the recommending should not be invasive to the users. The results of the recommending should be as pleasant as possible for the user, because the negative factors of recommender systems are well known. It's some aggressive ads and so on. So there are also factors that must be taken into account to do not recommend aggressively, because from the nature of the problem, recommending is not activity that is demanded by the user. It is something that happens within the application, so it must be really done harmlessly. And this is a really different situation when compared to querying, where the user really wants to query, so the user gets the answer. But here, when the information gets by itself to the user, the presentation must be very careful. Okay, so the basic loop of recommender system is these three steps. First, the recommender subsystem must collect some user feedback or some basically track of the user within the system. It could be either explicit or implicit feedback. I will talk about that. Here in this scholarly example, we just can suppose that user just ranks movies in this case. So the system learns preferences of the user with respect to the films, and based on these preferences, a preference model is constructed and used for recommending other stuff that the user didn't rank, and these unseen things, items are recommended to the user as new objects. As I said, the users could provide the feedback explicitly or implicitly. Explicit user feedback is really straightforward and understandable for any end user. Mostly, it's a kind of rating using stars like this, or just or other explicit, basically quite categorical ranking of a content. So if we are asked to rate something, we are using something like this. This explicit ranking has some pros and cons. The pros definitely are that if the user is explicitly asked to rank something, we are quite confident, or we expect that the user is confident that the popularity or the rating is really relevant for the user, because the user does it by himself or herself. So the advantage is precisely stated preference. I just say it's 3 stars and it's 3 stars. The cons is that this is not always guaranteed, because not all users are willing to give explicit feedback, and therefore it could not be supposed to be provided complete. So this is not complete. It's also subjective and inconsistent, because this rating is heavily dependent on the psychological effects and the time. So temporal effects, the same user can rate the same thing differently in different time, different moments in time. So this is the problematic concerns about explicit feedback. It is also a problem in e-commerce, because I can give explicit feedback after I have experience with the item. So in the case of e-commerce, it basically means I can give feedback after I buy something. So it would not be very responsible or serious to give ratings before I can really experience the item, the product, or event or something. So this not only could be problematic in terms of trustworthiness, but also in the view of scalability, because not every user can really buy thousands of products in order to rate them. So this is problem. Not enough quantity of ratings using explicit feedback. That's why the implicit feedback, the other category, is nowadays heavily used, because it removes the disadvantages of explicit feedback, but also brings some other problems. But okay, implicit feedbacks mean the user is tracked within the application during the user's normal behavior. So the user is not forced to give feedback. The user is just left to do the activity that the user is used to do in the application. For example, if the user is browsing in eShop some products, the user is just browsing, and during this browsing there are observed some interactions that basically can aid the system what's the preferences of the user. But this is kind of noisy data, because we can observe many interactions. So that's also the problem, what to track. We can observe the time the user spends on a page or object, number of visits of the same product, for example, or the same page, the zoom of something, number of mouse clicks, number of hovering mouse, number of scrolls down to details of products, and so on. So there are many interactions that are kind of very low level, and the lower level of these interactions are just moving a mouse quickly or slowly. What does it mean? The lower this kind of information, the harder to interpret this interaction as some meaning towards basically opinion on the subject of the rating of the feedback. So it's really noisy outcome out of implicit feedback. Of course, there is a huge advantage because this is for free, and every user that somehow interacts with the system, like eShop, gives implicit feedback. So it's really not a question of existence of this data. We always have this data, and moreover, these data are always objective, because the user doesn't interact with the system for the sake of user feedback, but just for the sake of the activity of the application. So for buying a product, for example, this could be a problem for the explicit rating, that a user could fake rating just because the user wants to get rid of it quickly or something, just provide some dummy annotations and so on, and these data are also not very valuable. In the implicit case, this is not so big problem. Okay, so explicit and implicit feedback, that's the key to recommend the systems. Now we will shortly introduce the methods of recommending, and out of 4 I have listed here, I will more closely discuss the first 3. So collaborative filtering, which is based on measuring similarity of users, but only on the principle of similar rating of items. So there is no very deep insight into the item properties. It's really designed only as a similar pattern of ranking of one user and the other users. Therefore, they are similar, and therefore one of the user could basically extrapolate from the user's rating to the other user's rating. Then the second is content-based recommendation. Here we already look into features of items, and this is beneficial when there is not much interaction between users and items, as is supposed for the first case. And the third is knowledge-based recommendation, where none of the 2 above is sufficient. So there is not much interaction with items, not much rating, and also features that are used in the retrieval are not basically available or are not enough when recommending. So therefore, knowledge-based recommendation comes into place. The fourth I will not really talk about is also demographic recommendation, but it's basically quite straightforward because it's based on demographic classes like age, gender of the user, and so on. And for different classes, different items apply. It could be used as a pre-filter of a huge set of items. And of course, many methods combine these and make a hybrid solutions. Mostly or very frequently, the first two are combined: collaborative filtering and content-based recommendation. This table gives us a quick comparison of the techniques with respect to three aspects. So the collaborative filtering models the problem using, or the input that is required for collaborative filtering is in form of user to item matrix. So we have a matrix of ratings of users to items. So it's kind of similar. We have terms by document matrix in vector space and Boolean model. Here we have another matrix, and this matrix means all of the users that we have could rank all of the items that we have. Of course, not all of them will rank all of them. So again, this matrix will be sparse. Again, the same property as we already had in the vector space model and everywhere basically. But this is the data model that is worked. That is the basis for the collaborative filtering. Yeah. So the source fills the model using by the ratings, and the method is to identify similar users just using the ratings, and then there is a prediction of ratings for another for the active user done using the ratings of the similar users if they did so. So of course this is some extrapolation from known values to the unknown. So that's basically the principle of collaborative filtering. The second technique is content-based recommendation, where we also have some ratings, but just for the active user, for the user for which we want to recommend something. And instead of simulating similarity of users based on ratings, we use similarity of items based on content features. So this is beneficial in cases we don't want to be dependent on other users. We just have one user and we want to recommend to the user items based on content similarity of items, not users. And at the end, the goal is to generate a classifier that provides the classification based on the user ratings for the active user. The third technique is, as I said, knowledge-based, and it's used in cases where we don't have simplified input like ratings or just features. We have some specific user needs that might be somehow represented. It could be either by knowledge base or by it's always by knowledge base, but it could be by some conditions and constraints, or it could be by some examples. So it depends what's available. And again, the item features basically are used for retrieval of or for recommendation based on knowledge-based model. So there is an inference of a match between items and the user's needs. So instead of, yeah, we have the knowledge base here and the features here, and we do some match. And the last is the demographic one, as I was discussing. It's not much to discuss about. It's about just demographic attributes, and this works basically like a binary filter. We can also extrapolate from binary filter to similar uses based on demographic attributes. For example, we create categories of, I don't know, young females, and they have probably similar interests, but this is just demographic, rough demographic recommendation. It's better to use this as a filter, not as the ultimate method. So the first one is collaborative filtering, and basically this method is based on annotation of items by other users. We don't need any information about the items themselves. We only need rating from other users to these items. So that's why we have the metrics of ratings from users to the items. And based on these items and based on these ratings, similar users are identified, and in those ratings where the similar users basically are known, the rates of the users are known, and the rating for the active user is not known, then these are extrapolated to the active user. Here we have used the term active user. Active user is a user where which is the one we construct recommendation for, or the others are the similar users to the active user. Basically, what we want to obtain is something like this. This is just a piece of Amazon result, and this is recommendation for an active user. And as we can see, these are 3 books about photography, and this infrared filter, again connected with photography, and apparently this result using collaborative filtering comes out from the previous activity of the active user, that the user probably bought something about photography. There were other users that also bought something about photographies. The active user has had in common some items that they all bought, but some of the users bought something extra, and these extra things are the recommended ones. This basically the reason, or the way the collaborative filtering works, because the active user didn't buy or didn't see these items, but other similar users did. So that's why it's recommended. Okay, so this is how it looks at the end. So now how it looks if we detail the method. So let's have this running example. We have a small matrix of ratings of 4 users, 2, 3 movies. We have Inglourious Basterds, Hunger Games, and The Alien. And we have ratings of 4 users, Peter, Dana, Michael, Bob. And we have 3 types of ratings, or 2 types and 1 non-rating. So we have like and dislike, and not available if there is no rating at all. And if we create a question like this, like shall we recommend Alien to Bob, and we look at the closest or most similar other users to Bob, which is apparently Peter and Michael, because they are similar in ratings to Bob, because Bob in case of Inglourious Basterds liked that movie, the same Michael and Peter, and the same for Hunger Games. Bob liked, Michael liked, Peter liked, but Bob didn't rate The Alien, so that's why we are asking for the question of recommendation. And in this case, both Peter and Michael didn't like that movie. So intuitively, from this pattern, we should not recommend Alien to Bob, because the most similar users to Bob, Peter and Michael, are very similar in the other aspects, but in The Alien they didn't like it, so we probably should not recommend it to Bob. So this is the intuitive example how to do collaborative filtering. So we don't know anything about the items, we just have ratings. In a picture we can visualize this principle really easily. If we have 2 users, just 2, and they are similar just because they did similar ratings. So rating in this case is buying things. So this user bought a pizza and a salad, and this user also bought a pizza and a salad. So in terms of pizza and salad, they are similar because they bought both, so they are similar. But moreover, this user also bought Coke or some soda, and this user didn't. So because these are similar based on pizza and salad, this Coke could be recommended also to this user, and this is how the collaborative filtering works, because this soda was not seen by this one, but was here, and that's why how we transfer this recommendation to this user. When it comes to the computing and making the method formal, we can use either user-based collaborative filtering or item-based. And we have nearest neighbor algorithm for this, and we could model similarity between users or similarity between items. So the first is similarity between users, where we first need to determine the mean vote for user I, and it's computed as the basically average vote for that user. So we take the set of items that the user I has voted for, somehow ranked. So we have a vote for the user I and item J. So we go through the index J through all the items ranked, and we divide it by the number of ratings, or all the items that were ranked by the user. So we get the average vote for the user I. And then if we want to predict a rank of an item J for an active user A, so we want to predict the score for item J for active user A, we compute it as a average vote for A, computed like this. And then what's more important now, why we even do this computing the mean vote? Of course, this is because of normalization of the scores or of the ranking, because some users tend to overrank or overscore items, and some tend to underscore the items. So relating the votes to the average vote is some normalization factor. So that's why we are using mean vote. So here we use as a basis, as the mean position, as the average rating, which is the initial hypothesis, the average vote, and then we accumulate basically votes of the most similar users to the same item. And how we do that? We compute the similarity of the active user to another user that is among the n most similar, that's pre-computed. This function W computes basically the similarity of the two users, and this similarity of the two users acts as a weight how seriously should be taken the contribution of the user I to the vote of item J. So what's the contribution of the user based on similarity? So as you can see, high similar users to A also have high weight, so their opinion is more important than opinion on the same item of a user that is not so similar to A. So that's the weighting component here. And again, because we need to somehow normalize the voting, we take the vote and subtract the average vote for the respective user. So we are using just this delta, and we compute it for n similar users, and then use some normalizer kappa that basically does averaging of this cumulated vote for that item. So now we have the way how to compute for every active user and every item the predicted score or rank of any item. Now how to compute the function W is here. We must compute the similarity of two users, A and I, and this could be done again by cosine similarity if we take two users as two vectors in the ranking matrix, but just on the dimensions they are really sharing some rating, then we can compute the cosine similarity. Because we cannot just take the whole vectors of the matrix, because in some dimensions, in most of the dimensions, they are not defined values, because as I shown in this example, here it's not available. It's basically not it's not complete metrics. Here we have just 10 values, and these 2 values are not defined. So if I compute similarity between Dana and Michael, I only can use dimensions for Hunger Games and Aliens, and I cannot use Inglourious Basterds because I don't know that for Dana. So that's why in this cosine measure it's used only the dimensions where both of the users have some rating. And based on this, I compute the similarity of users based on their rating to shared items. We could use also person similarity instead of cosine measure, where also the averaging takes place already in the similarity function. It's not just in the user-based algorithm, but it's already here, and it works again as a normalizer. So this is collaborative filtering based on the users. The other method is item-based nearest neighbor collaborative filtering algorithm that does orthogonal method or inverted method. Instead of computing the similarity of 2 users, we compute similarity of 2 items or of items generally, and do the prediction not based on similarity of users, but similarity of items. But basically it's the same matrix, so it doesn't matter if it comes from the vectors or from the columns. Okay, so I can see that intuitively these 2 items are very similar in the dimensions, in this case in the users, where they are both filled up. So in Peter, in Michael, and in Bob, they are like, and for Dana, where there is only rating for Hunger Games, there is 1 dislike, and intuitively we should also predict dislike into Inglourious Basterds. So if we ask a question, if Dana will likely to prefer or not Hunger Games, we should predict that it will not the case. So we do not recommend Hunger Games to Dana. But we see that we do it now column-wise, not row-wise. Okay, so this was collaborative filtering. The problems with collaborative filtering are related to the metrics, of course. The problem is if there are no or little data, little ratings. So if there are 2 sparse matrices. So when there is no rating for active user, basically what can we do? Because we cannot find any similar user if there are no user from active, there are no ratings from active user. Or the other way, if there are no other users than the active user, again there are no recommendations because nothing to compare with. So the data sparsity is the biggest problem. It is also connected to so-called cold start. Cold start means we are beginning the application, resetting the application where there are no rating at all, but it must somehow start to work. And how to do that if we have no data for recommendation? So this is the problem. So it must be solved by other method of recommendation. That's why these methods are combined together. Other problem connected to the practice of usage of recommended systems. If users have only a single session, so we cannot rely on some training phase where the user has the time to interact with the system, to give ratings, and then sometime eventually the system will start to recommend because the system gathers enough information about the user, so it can luckily now recommend something. So this is problem because no user will wait ages for starting the functionality that he expects immediately. What is interesting, that the collaborative filtering might not work even if there is enough data, because for some items that are controversial or some really have some really non-deterministic statistics in the population, this prediction could be completely wrong. For example, if we have two users that have 1,000 of rating in common and they are all the same, so these are super similar users, one item that for one user is rated somehow and for the other users it is not rated at all, and we predict this rate, the rating would be completely different because this item is really splitting population into two extremes, for example. So it's loved versus a hated item or something like that. There is no smooth distribution, but there are two peaks, completely reject and completely accept. So this is problem of collaborative filtering, because the resolution collaborative filtering is just statistically on other ratings, and we do know nothing about the just predicted item than the context of other ratings, nothing else. So this is general problem of collaborative filtering. Some partial problem could be expensive calculation of similar users, because there are many of them. The matrices could be huge. We are used to have huge matrices. So this could be solved by sampling or clustering, indexing the data. So this is not of much problem. There are more serious problems like this one. What we can do to make the metrics more dense, if you think about it, what we did in vector model of text retrieval, we did some dimensionality reduction using the latent semantic indexing, or SVD or PCA, whatever kind of dimensionality reduction method, and we got from very sparse metrics to very dense metrics. So this could be also the case for collaborative filtering, to get more dense matrices by reduction, dimensionality reduction. But if the metric is really very sparse, this will not help us anymore. So in such case, we must resort to other methods that basically somehow allow us to dense or populate the metrics more. And recently, these approaches, as in other subjects, are realized using machine learning. And in particular, for example, we can in machine learning, the common technique is to simulate users to rate. So we have some simulated users that rate the things based on some other learned model that is transferred from one domain to the other domain. So this is a classic case of transfer learning. If we have or well mapped domain, or we have enough data in one domain, we could try to transfer this knowledge to other domain where there are very sparse data. So using simulating users and rating from one domain to the other. So this is generally what it's tried to do using machine learning, for example. Okay, so that was collaborative filtering. The second category or method of recommending is content-based recommending, and it's useful in cases where we don't have enough rates. So that's the problem of collaborative filtering. But we do have another knowledge instead, and that's features of the objects themselves. So instead of finding similar users and recommending the missing votes from the other users, we try to find similar items to already ranked items and recommend these ones. So this is the prototypical example. We have user Homer that already bought a beer DAF, and this item, this beer, is similar to another item, this T-shirt, because of something. It doesn't matter. It's based on the features. For example, it's the same brand. It's DAF, and it's again DAF, and it's red, and it's red. So therefore, that's similar. It doesn't matter what is the similarity model. Of course, it could be very many similarity models, but using some similarity models, these are similar. and maybe the t-shirt is the most similar to the beer out of all the items in the database. So this is the first nearest neighbor to the beer. And therefore, the because of the similarity, there is a recommendation scope score computed, and this t-shirt could be recommended to user to buy it. Notice that we don't need any other user. We just need rating for Homer, because we must know something about the user. If we don't have any information about Homer, we have no material to recommend. So we know one thing. We know that Homer bought Duff, and we can compute that Duff is similar to this, and this is something that Homer didn't bought yet, so we can recommend it. So this is content-based recommendation. The recommendation is based on finding the k nearest neighbors. So in this case, it was the first nearest neighbor, but we can have more objects than just one, and recommending those out of the k nearest neighbor that the user didn't see yet. So of course, we will not recommend something that the user already ranked or rated. So because we only can recommend unknown stuff. And for the measuring the similarity itself between the content, between the items, we need to use some content-based similarity measuring, and depends on the similarity model that is established for the items. If there is only this visual information known, there is no annotation, we could use some visual similarity between the layout of the colors, for example, or if there is some textual annotation attached to the items, we could again use the vector model by words. So for full text similarity, we can measure by cosine measure these two items, their text, and depends. So we can have different features extracted out of the items. So for multimedia, as I said, there could be used symmetric distances. We also will discuss this in next lectures. If we have very simple representation of the features, like a set of keywords, for example, then we can use super simple Jacquard coefficient that just measures the proportion of the overlap of these two sets to the union of these two sets. So if there are many keywords in common in the descriptions, then the Jacquard coefficient would be high, and therefore the similarity would be high, and therefore maybe it will be recommended. So if there is just one, there are maybe two keywords. There is Duff and beer, and here are two keywords, Duff, t-shirt. They have just the Duff in common, so there is similarity 1/2, but maybe it's the high similarity found, so it is recommended. Okay, so this is content-based recommendation. Then we can formulate the recommending problem as a classification problem, where we finally want to get the final result, the decision, if we should or should not recommend the item based on the features. So the rating could be like this, like or dislike. So this is another step after determining the k nearest neighbor. So we have the classification step. Of course, for classification we can use number of techniques from machine learning again. Now the advantages for content-based recommendations are, as I already mentioned in collaborative filtering, the independence to other users. So we do not need any other users and their ratings to start recommendation. We just need the active user and the active users recommended ratings, and then just the features of the items. It is also more transparent because it gives us some better explanation of the recommendation. Because if we look again back to Homer situation, we can say, okay, I recommend the t-shirt because similarity to other product, and this is something that is quite semantic. These two items had some features in common. For example, it's Duff, this is Duff, so I can explain it better. This is different from the collaborative filtering, because then the explanation only would be okay, I'm recommending this because you are really similar to other users and they just were recommended by that, but I don't know why, but they were. So this is not explanation based on the real content, but just about the context other people chose this. So there is better explainability. And another advantage is that we can really immediately include new items into the recommendation. So we, because the process of feature extraction is automated and it's done right after a new item is added to the database, we have not a problem with cold start like in collaborative filtering, because in collaborative filtering, when we add new items to the collection, we must wait after some users rate this item to be able to recommend this item. And this could take ages. But in content-based filtering, this is not a problem. We can immediately compute similarity on the features and really put this item into the recommending process. Of course, there are some limitations or drawbacks. The feature extraction as a process is again is questionable, because we might not have perfect feature extraction model and representation model of the features. So this is some uncertainty, another that comes into play. It's heavily dependent on the domain, and maybe if we rely on annotation, not only on the content itself but also annotation, this could be missing. That's the reason. If we want to have textual annotation here and here and make the similarity based on text similarity, when it's missing here, we cannot use it. But this is also a problem with collaborative filtering if we miss the ratings. Another specific problem of content-based filtering could be over-specialization when we have two similar items. Again, with the example with Homer, if there is Homer bought beer, and there might be other kinds of beer that are really very, very similar to this beer. Maybe this different percentage of alcohol or something, very, very slight differences between that. And because the other beers are really similar to this beer, they will be recommended to Homer, because it's the best match in terms of similarity on features. But basically, from the conceptual point of view or semantic point of view, we are recommending just duplicates, because there are so slight differences between different kinds of beer in terms of the whole world of other items, that the Homer gets no new item recommended, because it's almost the same beer. So in this case, we would like to favor something that is not so similar, but this is a different problem. And last problem is with the new user, where the user does not have any ratings given, so we must collect first the ratings. But this is also the problem of collaborative filtering. The last category is knowledge-based recommendation. That is specific to some application domains where there are not frequent purchases of items and very few ratings, and this is quite specific for expensive items that really need careful thinking before the purchase, or professional items. So if somebody is wanting to buy a house, he will probably not be satisfied with collaborative filtering. First, because the other users probably did not buy the exactly same house, and also we probably want to have much more validation on this expensive item than just some house recommendation or some rough features like I don't know, the square meters per room or something like that. So this is something that doesn't work with neither the collaborative filtering and nor the content-based filtering. So for this, we need something that is more sophisticated, some knowledge-based system. The same for personal items. If a surgeon needs some instruments, instruments probably will not have enough recommendation by other surgeons, probably, or other tools that are professional. Also, there is a problem of time span between the products. I can have enough scores or votes, but in the time that I'm now, there are only little of them. So because the technology is developing, and I want the most up-to-date item. Okay, so in this case, both collaborative and content-based filtering are insufficient, and we need some more expertise into the process. So this is the time for knowledge-based recommendation. In knowledge-based recommendation, we either rely on constraints that are exactly defined conditions to satisfy the recommendation problem. So this basically is formulated as constraint satisfaction problem, or we don't have, or we cannot formulate these conditions, so we resort to case-based knowledge-based recommendation. So we have some good examples and we relate to these examples, so we measure similarity to the case of what we recommend. So in this sense, it's a bit similar to content-based recommendation, but it's more complicated because we measure the similarity to the knowledge, not to the individual items. So the requirements, similarity to requirements, not to item. In the first case of having the constraints, let's have this example. It's from the financial domain, and we have six objects. We have the set of customer properties, we have the set of product features, we have the constraints on customer properties, and we have conditions on the relationship between customer and products, and finally we have the possible recommendations as the final set. So what we can have here, so this is the properties of the user. So the user can have different properties in different features. So the level of expertise of a user that is involved in financial investments could be expert, average, or beginner. The user can take more or less risk. The user wants to invest in longer or shorter periods of time. He wants or wants not advisory, and so on. So, or type of investment, and so on. So this is the available features for a user, how the user is modeled by the combination of these values. The same is for the products. So products has these features. So name of the product, expected return rate in months probably, risk level high, medium, low, and minimum investing period in years. And the next is the constraint on the customers. So we just do some constraints on the combinations of all these values. So for example, if I am beginner, I probably cannot risk too much. So my willingness to take risk cannot be high because I'm beginner. So this is just very, very basic constraints. There are more constraints on the products or on the filter conditions between the products and the users. So for example, if the user wants to invest in short term, then the product property should be less than 3 years. If it's medium, it should be between 3 and 6 years, and in long term more than 6 years. Again, when the user is beginner, then the product cannot be of type high risk, and so on. So these are other constraints. And finally, when we infer from all of these combinations the possible combinations that we have, and that's the recommendation, we for example get these 3 options. So if the risk should be low. Probably it's good to just put the money into saving funds for 3 years, a minimum for 1 year, for example, and so on. If we want high risk, it's something else. So this is some example of how the knowledge base could look like and how the inference could be done. Of course, the development of the knowledge bases is not easy, as we can see in this very simple example. It will be probably very difficult and expensive process to build such a knowledge base using specialized tools. Probably it's a kind of programming, basically. Establishing such a knowledge base is a kind of programming of rules, and involving rapid prototyping, detection of invalid constraints, testing, and so on. So it's more similar to development of software than just putting some rates or something like this. We can have problem of unsatisfied constraints, and this is something that is really similar to Boolean query of text retrieval. We have experienced zero results when we put too restrictive Boolean query. If we end everything, then we really cut the candidates to 0 set. So we have the same here. If there are very strict constraints chained, then we can end up with an empty result. So in such case, we must somehow relax the constraint, and this is quite difficult, because the same as in Boolean query, how to relax constraint when the constraint was designed to be restrictive, but it cannot be. So that's basically a big problem. And last but not least, the user needs some guidance in the recommendation process, some elicitation process, some dialogues with the users based on the user profile, also some recommendation, and so on. So this is much more complex process or recommendation. Okay, this was the 3 categories of recommending methods, and now we skip to social information retrieval. As everybody knows, the social media are omnipresent now, and they, from the database or computer science point of view, they bring explicit graph informations or network information into play, so the retrieval algorithms can use this information. So we already had this for PageRank, but now we can really use quite a high level of abstraction on the data type. So we have not data types, simple data types like text or word something. We have data types like user profile, posts, likes, friend, and so on. So these are just interpretations of new data types, and basically the fundamental data structure is a graph or multigraph. We can also have inferred social networks, as I mentioned, that are not explicitly defined for the end users, but that are constructed from other third-party data, and technically this is done by some database operators like spatial or similarity join. We'll talk about joins in later lecture, and this is obviously constructed for some domain-specific purpose, because we need to reconstruct some underlying social network out of some other data. Of course, because this is done not explicitly by the users themselves, this must be treated by some legal issues, because this is something that the users basically do not know beforehand, so they must agree with usage of their data for these purposes. I have 2 examples here. One is very up to date. Today or in the next months, we can expect that there will be developed smart methods for localization of COVID-19 suspects, and this is exactly what could be named as inferred social network. So if we take some data from mobile operators, where we have phone localized data from some transaction log of them, and we do spatial join on this data or self join, we can identify people that were in contact with people infected by the disease. So we can really create inferred social network of people that are somehow in a relation, and this relation is the closeness to other people that are suspect. So this is one possible example of inferred social network. The other is maybe more business-based case, and that could be a network of bank clients, but not as some bank Facebook, but again created, constructed from the transaction data, where we have, for example, credit card transactions of bank clients, and we can again join these transactions or transaction log to get similarity between the clients and to connect clients that are somehow similar to each other. This could be visualized like this. We can have the classic relational data, the transactions about the clients. About the clients, we have some demographic or rule-based data that we can use for construction of some kind of relations among the users. And from the transactions, we have another information, basically the behavior of the clients with respect to their financial instruments. So they somehow, for example, pay by credit cards, and therefore we can also measure their similarity based on this. So we can finally construct an inferred social network where, for example, one type of this edge is of type is the similarity based on the financial transactions. So for example, these two persons, Adam and Larry, maybe go to the same ATM to withdraw money, for example. And this another edge is another kind of edge. It comes from the demographic data or other data, and this is, for example, a relation because these two persons basically not these two persons, but these two persons, Larry and Martin, share the same workplace because they have shared institution, that is our faculty, and this is connection to the faculty from one person, Larry, and this is the same connection with Martin. So we can collapse this node, and we can see that Martin and Larry are connected by this kind of locality relationship. So, and we can add to this inferred social network many other kinds of relations, and finally we get some very rich multigraph that we can use as a social network and traverse and segment it and identify communities and whatever we want to do. So again, this is another approach to social information retrieval. Another example of how we can reuse of what we already defined is the PageRank. We have defined PageRank for web pages or for resources generally, and we could reuse it in the context of social media, because instead of graph of web pages, we have graph of users or graph of posts or graph of any other entity, and we can compute the same because we just need for the PageRank computation just the topological information of the graph, no matter what it actually means, and we can compute PageRank of for example, a user that is cited by other users, so the user will have a high social PageRank, or the user's tweets. If it's retweeted, basically it's getting in links, or if I have very many likes, I'm receiving very many in links, and in links are basically the power how to boost the PageRank. So we are in completely different context, but again it's a graph-based context, so we can reuse construction of PageRank for different purposes. Also, we can use other specific tools for retrieval of information from social media. It's very popular nowadays to use hashtags. Everybody can use hashtags, which is something quite technical. So it's very nice that even end users could really use hashtags as unique identifiers of entities. So nowadays it's really easy to just search using hashtags because the users are really cultivated to understand what's hashtag. So this is another tool that appeared in the context of social networks or social media. So the graph structure is something that is in common to both social media and other graph-based applications or models, but of course the the interpretation changes. So instead of referring one web page to the other, we can create an edge by liking content, retweeting content, following some user profiles, friending, unfriending, and so on. And this this could also serve in combination with the collaborative filtering or content-based filtering, because if we are liking something, we are basically rating the content. So in the context of social information retrieval, there is quite nice symbiosis between recommender systems and the features that the social media or the data model in social media allows. So we have graph information, but we can convert it to metrics information. So for collaborative filtering, it's a huge opportunity to benefit from the graphs of social media, and so on. We can experience global and local trends because we can identify the people also by the demographic attributes and so on. So we have a huge combination of many techniques in social media that blend together in a huge hotpot, and the social media is very fruitful environment for all of the methods of personalized retrieval. Here we have this relationship just formalized or formulated. Recommender systems definitely bring benefit to social media because they allow to filter and recommend content to the users of social media. And on the other hand, the recommender systems benefit from social media, as I said a while ago, that they really can use the annotations, graph-based annotations like tags, comments, likes, and relationships, basically as the material for rating and collaborative filtering, for example. Okay, so this will be the last slide. Of course, we must take into account also the negative sides of personalized techniques. Basically, there could result in annoying ads. So this is something that I mentioned in the beginning of the lecture, that the presentation of the recommendation to the end users must be done carefully, because it could easily get really annoying because it's not explicitly demanded content that gets to us from recommending systems, but it's something that we might or might not evaluate as an information value. Okay, so that's it.